Okay, so let's update what we know on our figure, and then we can start to use our equations. So we know first that during the compression process, U2 equal U1. When we say this, okay, so the energy, if you want, at 1 is equal to energy at 2, okay, internal energy. So this will give us an information about process 1, 2, okay. Now, concerning from 2 to 3, we have constant volume. Because it's at constant volume, so whenever we want to calculate the work will be 0, because you know that integral PDV will be 0 since volume is constant. So here work from 2 to 3 is equal to 0. They gave us the value of work from 3 to 1. So from 3 to 1 we have expansion. So the work is positive because it's done by the system. So from 3 to 1, the work is equal to 10 to the power 5 kilojoule. Okay. And we have that for the whole cycle. For the whole cycle, we have W cycle equals to minus 8.3 kilojoule. And we know also that the volume at state 1, so we know that V1 is equal to 1 meter cube. So this is what we know, and we want to determine the work and heat transfer for processes 1, 2, and if it's a power cycle or refrigeration cycle. So we'll start to do calculations step by step. As we mentioned, we say first, we start from the first process, okay? So we say first, we know the value of W3, and during process from 3 to 1, the pressure is constant and we know its value. Okay, since we know its value, we start to say W31 is integral from state 3 to state 1 of PDV. And because it's a constant pressure process, you can take P outside of the integral. Okay, so when you take P outside of the integral, then you can find the value of an expression for V1, function of V3. So as a first step, from W31, we can calculate the value of V1. Then, to find the work, okay, we know that W cycle, the total work in the cycle, is the summation of work in the different steps. So work of cycle, total work of cycle, is equal to the summation. Sorry, just 1 second. So W cycle is equal to the summation of W from 1 to 2 plus W from 2 to 3 plus W from 3 to 1. And just pay attention, please, for the, if you want, for the signs, okay? Here, W cycle is given. And also, we have W31 is also given. So we just have to replace it. And we said that for the process of constant volume, okay, which is W from 2 to 3, we have no work. So the only unknown in this equation will be the work from 1 to 2, okay? Since they gave us that W cycle is negative, so we replace by a negative value, and W31 is positive, it's plus 10 to the power 5 because it's expansion produced by the system. So this equation will allow us to calculate what is the work between 1 and 2. And as expected, we'll get a negative result. Why? Because if you observe the graph, you can see that from 1 to 2, you have compression effect. Okay, so the work is done on the system, so you can expect to get a negative result for your work. Now, in the last step, we want to calculate also before the last step, we want to calculate the heat transfer between 1 and 2. Okay, so during this process, they gave us that the internal energy is not varying. And we know that we can calculate the at a certain state, okay, between state 1 and 2, we can write that delta U, and as I told us, please pay attention for something. When you work on a closed cycle, for a closed cycle, delta E is 0. But when you take each process alone, for each process, delta E is not 0. So if you go from 1 to 2, from point 1 to point 2, you have variation in energy. Okay, but when you go back to 1, between point 1 and 1, no variation in energy, so delta E is 0 because you are going back to the same state. But when you go from 1 to 2, you can write that delta E from 1 to 2 is equal to Q12 minus W12. Okay, W12 was already calculated in the previous step. So, and for delta E between 1 and 2, we can say we can decompose it into variation into the internal energy plus delta kinetic energy plus delta potential energy. But they told us in this problem that you can neglect any variation in kinetic and potential energy. So these two terms will cancel out. This is 0. This is 0. And also for process from 1 to 2, delta U is 0 because U1 is equal to U2. So we deduce here that Q12 is equal to the work between 1 and 2, equals to minus 18.8 kilojoule. So we have heat loss through this process to the surrounding. And now to answer the question if it's a power cycle or not, if you remember, what should we do?
نشوف ال W cycle.
Yes, exactly. بدنا نشوف ال W cycle. نحن تيكون power cycle مفروض يكون عنا
Positive.
generation of work، صح؟ يعني تنقول it's a power cycle we have production of work. مش العكس. نحن قلنا بالrefrigeration cycle or heat pump, we put electrical power, let's say, to force heat to go from a cool place to a hot place. Okay, so in case of refrigeration, W is negative because we put work. But in case of power cycle, we put heat to produce work. Since here we got a negative work, this means that we are putting work on the system, so it's not a power cycle. The power cycle should have W cycle positive because in a power cycle we produce work, so the net work is positive according to our convention. However, here since we got a negative result, so it cannot be a power cycle, but it is a refrigeration or heat pump cycle. Okay. Any question on this? Another problem. The following table gives data in BTU for a system undergoing a power cycle consisting of 4 processes in series. Determines the missing table entries and the thermal efficiency of the system. So we have information, okay, for different processes, and we want to complete any missing information. So as usual, okay, always for each process, we can say that delta E is the summation of delta U plus delta kinetic energy plus delta potential energy. Okay, so here, for example, we should have here 50 plus 950. So it's 1000. So this is delta U, and then delta E. And then we can say that delta E is equal to Q minus W. So for example, here, if we apply it for the first process 1 to 2, since delta E is equal to Q, this means that W is equal to 0. Okay. Now, for process from 2 to 3, we know delta kinetic energy, delta potential energy, and delta E. So now to calculate delta U, we just have to say that delta U is equal to delta E minus delta kinetic energy minus delta potential energy and then it's equal to minus 450 minus 0 minus 50. So it's equal to minus 500. So delta U is minus 500. And now because we know delta E and we know the value of W, we can get Q. We know that Q is delta E plus W. So because it's minus 450 and plus 450, so Q here is 0. Now, for process from 3 to 4, so similarly here, we can deduce that delta KE is plus 50 because the summation will give us minus 600. And since W is 0, so delta E is equal to Q, so Q is minus 600. And finally, for process from 4 to 1, delta E is the summation here, so 200 minus 150, it's plus 50. And since Q is 0, we know that delta E will be minus W, so W is minus 50. Okay, so now we were able to complete the table. Now, how we calculate the thermal efficiency here? To calculate the thermal efficiency, first we calculate W net of the cycle. Okay, so W net, so we said here it was 0. W net is 400. It's a positive value. Because it's a positive value, so this is so it's 400 BTU. It's a power cycle, okay? And then the efficiency will be equal to W net over Qn, okay? And the process in which we have an input of heat is the process from 1 to 2, because we have a positive value of Q. So all we have to do is to divide 400 by 1000. So the thermal efficiency of this power cycle is 40%. Okay. Any question on this? So here you have the detailed solution for the problem. Another problem, a refrigerator cycle operating as shown in the figure has a heat transfer Q dot out equals to 2400 BTU and network of 800 BTU. here we are putting work on the system. Okay, so it's a refrigeration system. And we know that in a refrigeration system, to calculate the coefficient of performance, we should divide the useful power. What is the useful power here? Is the refrigeration flux that you can take outside of your system. Yani you are taking heat from your system. So whenever we talk about refrigeration coefficient of performance, COP, we should divide, because it's refrigeration, so we care of the heat that is losing the system. It's Q dot out over the electrical power that we are putting to the system. So over W dot. Okay, and for COP can be larger than 1, not like the efficiency. The efficiency of a power cycle is always smaller than 1, but the coefficient of performance in refrigeration cycle can be larger than 1. And this is the case here, because here COP of refrigeration is 2,400 over 800. Okay, so here we get it equal to 3. The COP is equal to 3.
دكتور إذا
Yeah,
تكون
sorry,
QN
no.
على
Look,
W cycle.
we should calculate the net. Yes, exactly. Look, we should calculate the net value. Okay, and here, because they just give us, if you want the value of Q out, but we need to divide by QN, because we QN is, يعني Q that is out هي rejected للهوت للسراوندينج. نحن بدنا الكيو اللي بنشيلها من جوا. اوكي، so just pay attention for this. هن عطونا مش this one، ما عطونا الكيو اللي طلعناها من الاندور environment، عطونا الكيو اللي كبيناها لبرا. اوكي، نحن بدنا نجيب الكيو اللي طلعناها من قلب الانفايرمنت. so what we should do then، اوكي، نحن عندنا اذا بدكم الانر سبيس والاوتر سبيس. انا فكرت الفاليو اللي اعطونا اياها هي اللي اخذناها من الانر، بس no, they just gave us Q اللي كبيناها على السراوندينج برا. okay, so they gave us Q rejected اذا بدكم to the surrounding. نحن we should find Q اللي اخذناها من الانر space. okay, and when you cool, your purpose is to take heat from the inner space at height which is at a relatively cooler temperature, and reject heat to the surrounding. هن بدل ما يعطونا just this flux directly, they gave us the outer flux. okay, يعني هن إذا بدكم just عطونا ال Q out، هن سموها Q out. يعني قصدهم كبيناها للسراوندينج، مش قصدهم Q out أخذناها من ال inner environment. okay, so again all of these will be clearly stated in an exam. okay, so here you just have the Q that you are taking from the space. I will call it Q inner. okay, to find the Q inner, you need to write the balance for your system. The balance for your system is W cycle is equal to Q out minus Qn, because you know that when you take a closed system, delta E is 0. okay, and because delta E is equal to 0, equals to a Q minus W cycle. okay, for Q now you can decompose it into what is coming in and what is getting out. okay, so here if you want, if we consider a refrigeration system, we have a Qn is the one coming from the inner environment, yani from your room. So Qn minus what you are rejecting to the surrounding. So minus Q out okay, minus W cycle equals to 0. We should pay attention here, okay? W here, how we take it? W here is negative, okay? It's negative because we are putting work on the system. So بتصير minus minus, okay? So you get here plus 800. Okay, so you deduce that Qn is equal. هلا هن دغري اذا بدكم اخذوها in absolute value W cycle. That's why حطوها minus W cycle, okay? بس هي actually if we want to follow our convention نحن بنحط W as negative here. And we put minus minus بتصير plus. It doesn't matter how you take the convention, مهم طبقوها صح. إذا أنتم بتاخدوا W cycle positive يعني كأنه عم تاخدوا the absolute value of it, then you put here minus. Okay, so at the end you have that Qn is equal to Q out plus 800. And replacing Q out by its value اللي هي 2400. So here it's as we mentioned before minus لأنه for the negative sign. Okay, يعني إذا نحن بناخدها لتاني ميل تطلع minus. Okay, so Q out minus 800, 2400 minus 800 equals to 1600 BTU. Okay, so this is the value of Qn. So you are putting energy, you are putting electrical power in order to force heat to go from the cold body to the hot body. Okay, and as we mentioned again, just pay attention for conventions whenever these two fluxes are getting in of your system. So whenever you want to write the equation, you should respect signs. إذا نحن حطينا Q minus W, we replace W here by minus 800 فبتصير Qn minus Q out plus 800 equals 0. Okay, just pay attention for this. ساعتها when you take them to the other side بتصير Qn equal to Q out minus 800. And once you find the Qn, to find the refrigeration efficiency قلنا انه refrigeration efficiency بالاخر بهمنا قديش شلنا heat from the room. Okay, that's why the useful if you want the useful output of your problem is Qn, because you was able to take this heat from the room because you are doing refrigeration. لو نحن عم نشتغل heat pump كان بالعكس، كان بيهمنا قد ايه يعني بيصير بيقلب الكيس، بيصير برا هو هون بيصير السراوندينج لبرا، اوكي، وبيصير الروم جوا. ساعتها بيهمنا this flux Q out بيصير بيهمنا بالسي او بي. يعني لو كانت heat pump سي او بي بيكون Q out over W because it's a refrigeration cycle. السي او بي بيكون Qn over W, so it's 1600 over 800, which is equal to 2. So the COP here is 2. So this is COP for refrigeration. لو كنا عم نشتغل ب heat pump يعني we reverse the things. Okay, لو كانت heat pump COP heat pump بتكون Q out over W cycle يعني بتكون 2400 over 800 بتكون 3. Okay, but here it's not the case لأنه here the room is from this side, not from the other side. Okay, any question on this? Okay guys, thank you, we are done for today.
Thank you, doctor.
Welcome, bye bye.
Bye.